This is trigonometry, section 5.3, where we're going to be solving trigonometric equations. So this is going to require us to remember some things from last unit, from unit 4, when we were using our unit circle to find certain angles that had certain sines, cosines, or tangents. Also, we might have to use a graph here or there to find some solutions. So I've got Desmos pulled up. You may want to as well. So you'll notice that this is kind of our halfway point through the unit. We've done 5.1 and 5.2, which was verifying and using those trig identities. Today is definitely a very different type of approach. We're still going to be doing a lot of algebra to solve these, but we're going to kind of tie it all together with what we know about trigonometry so far. So as we go through this, I'm going to try to show you some tips and tricks on how to solve these types of equations. And as long as we follow the rules of algebra, right, whatever we do to one side, we do to the other, we should be in pretty good shape. So when you try to solve these, there are certain things that we're going to look for. We're going to try to collect like terms. So like terms being like all the sines, all the cosines. If we've got certain x's in certain places, you'll see. And then we're going to try to start factoring some of these. So remember, when we factor, we're going to look for things like a greatest common factor, or we may be even doing reverse foiling. So what you want to try to do is isolate the trigonometric function on one side of the equation. For instance, we want to get a statement that says sine of x is equal to 1/2. We've isolated the trigonometric function so it's all by itself, and then from here we can use, right, everything we know about our unit circle to determine what are the angles of x that will satisfy this type of equation. Here are some examples, right? If the sine of x is equal to 1/2, then my angles, notice they're in radians. We've got pi over 6 and 5 pi over 6 that are in the interval 0 to 2 pi. And you will see this type of notation. Remember, this means to include the number 0 because it has a bracket, and this has a parenthesis, so we exclude. So basically, it doesn't want you to give the same answers twice because 0 and 2 pi are coterminal angles with each other. Sometimes we may have to graph, right? Sometimes if we're looking for something like 1/2, where the sine of x is 1/2, we can easily look on our unit circle. But what if we get values that are not on our unit circle? Well, using a graphical representation where you say, okay, here's my sine curve, and I want the sine of some angle to be equal to 1/2. Notice they then plotted y equals 1/2, and you just find those intersection points that are on kind of the interval that you're looking for. And sometimes we won't be looking on an interval. Sometimes they'll want the answers to be so generic that you can write them this way. So you can say, well, pi over 6 plus any coterminal angle with pi over 6 will give you the answer. Or this one, 5 pi over 6 plus any coterminal angle is also a solution. So sometimes our solutions will be written like this, and sometimes we'll be looking for specific answers in an interval 0 to 2 pi. So here's kind of, again, that representation. So we know that the sine of pi over 6 is 1/2 and the sine of 5 pi over 6 is 1/2, but we have to consider every coterminal angle with those angles as well. So we're going to want to make sure we use exact values rather than decimal approximations when we get certain things like square root of 3 over 2, square root of 2 over 2. Remember, those are points that are on our unit circle. For points that are not on our unit circle, we can use decimal approximations. And hopefully once we do a few examples, you'll start to see the pattern and start to realize when you can and cannot use exact values. All right, so let's look at our first example. We are trying to figure out an angle that when I plug it in as x, it makes this equation to be a true statement, where the left side of the equation equals the right side of the equation. So what I want to do in this is I want to put all the sine x's on one side. Okay, so I'm going to add the sine of x to both sides. So I get sine of x plus sine of x plus square root of 2 equals 0, right? Because at this point I've added. Now I want to move everything that's not a sine of x to the other side. And I'm going to combine my like terms. What's 1 sine x plus another sine x? That's 2 sine x equals negative square root of 2. I want to solve for just the sine of x is equal to something, so I'm now going to divide both sides by 2. So the angles that I'm looking for that satisfy this equation have a sine value of negative square root of 2 over 2. So I'm going to look over here at my unit circle. Let me make it a little bit bigger so we can see. And I say, okay, my sine of x values that have negative square root of 2 over 2, right here and right here. So my solution for this is that x can be 5 pi over 4 plus any coterminal angle with it, or x can be 7 pi over 4 plus any coterminal angle with it. So those are the solutions. And if I want to double check, I can take, say, 5 pi over 4, if you'd rather use the degrees, take 225 degrees, plug it into this equation. And the left side will equal the right side. So these are the solutions that I'm going to be looking for on a homework assignment. All right, let's do our next example. 3 tan squared x minus 1 is equal to 0. I want to isolate the tangent of x. So the first thing I'm going to do is I'm going to add 1. So I get 3 tan squared x equals 1. Then I'm going to divide by 3. So I get tan squared x equals 1/3. I want to get tan x by itself, so I'm going to do the inverse of squaring, which is square rooting. So I get the tangent of x is equal to positive or negative, and I can't have, right, a radical in my denominator. So I get positive or negative square root of 3 over 3. So I've got to consider every single one, right? Because I've got to consider both positives and negatives. So if you remember, now I know tangent is not on our unit circle, but hopefully it's one that we have memorized. Remember, it's sine divided by cosine. So I have pi over 6 as one of my answers, 5 pi over 6 as another answer, 7 pi over 6, and 11 pi over 6, plus all of those coterminal angles that exist within them, because, right, it could be positive or negative. So I've got to consider all 4 of these answers. But I want to give a very generic answer that covers everything. So I'm going to say, well, x could be equal to pi over 6, and instead of adding 2 pi, I'm just going to add pi, or a multiple of pi. If I add pi, well, that covers 7 pi over 6. So just with this answer here, I've got those 2 answers covered and any additional coterminal angles with each of those covered. My next one, I'm going to do 5 pi over 6 plus any multiple of pi. So that is now going to cover these 2 angles and all of their coterminal angles as well. So there we have it. We have our 2 answers that give all of the solutions to this equation. All right, example 3. Ooh, we've got a cotangent and a cosine going on here. All right, so we are going to be factoring as we go through this type of example. Okay, we want to set equal to 0 first. Set equal to 0. Remember, I'm trying to give you some tips and tricks to solve these. We're then going to factor, and then we're going to set each factor equal to 0 and solve. So those are kind of our tips with this one. So I know that I want to first set it equal to 0. So I'm going to subtract 2 cotangent x from both sides. So I get cotangent x times cosine squared x minus 2 cotangent x is equal to 0. Now I want to take out my GCF. So what term is common to both of these terms? Well, it's cotangent x. So once I factor that out, I get cosine squared x minus 2. And if I wanted to, right, I could distribute this through to double check that I did it right. I did. So now I have it factored. I'm now going to set each of my factors equal to 0. So I get cotangent x equals 0, and then I get cosine squared x minus 2 equals 0, which is cosine squared x equal to 2, square root. I get the cosine of x is equal to positive or negative square root of 2. Okay, so now that we've kind of got our solutions, or what we want for a solution, now we need to figure out what are the angles that satisfy that value. So the first thing is, let's look at the cotangent of x is equal to 0. So remember, cotangent is going to be cosine divided by sine. And I want, when I do that, to get out a 0. So cosine divided by sine, that means I'm going to want a 0 divided by a 1, not the other way around, or else it would be undefined. So the angles that I see on my unit circle that have a cotangent value of 0, we've got pi over 2 and 3 pi over 2. And so how I can show that solution is I can do kind of what we did last time, pi over 2 plus, instead of 2 pi n, just pi n, because just that one solution there is going to cover both that angle and that angle. So we're covered. Our next one here, well, the square root of 2 is 1.414, yada, 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 something like that. Now on our unit circle, you'll notice there are no values of cosine or sine that are greater than 1. So therefore, or less than negative 1. So therefore, this has no solution. And if you wanted to double check, right, if you wanted to pick up your calculator, you could do inverse cosine, right, of square root of 2, and you will get an error message. It does not exist. It is outside the bounds of what cosine and sine include. So that is our solution for example 3. Okay, so we're going to get into some functions that look like quadratics. They are quadratics, right? It's just instead of x squared, we have the sine of x squared or the cosine of x squared or something like that. We are going to factor as much as we can. And when I say factor, right, we're going to reverse FOIL like that. So we try to get out our 2 parentheses. I'm going to warn you, we're going to do one example with the quadratic formula. You'll have one example on your homework that uses the quadratic formula. And I know you love singing along to the quadratic song, so we're going to definitely do that. But first, let's start out with what I would consider a more straightforward example. So we've got 2 sine squared x minus the sine of x minus 1 equals 0. And instead of finding all the multiples, I just want to find the answers that exist between 0 and 2 pi. So that's a little bit more straightforward. What I tend to do with these, to try to take out some of the confusion, I'm going to rewrite this in terms of just x's. Not in terms of sine of x's, but just x's. And I want to figure out, how do I factor this down? Well, I know I need to get 2x times x to get my 2x squared, and I need to get 1 times 1 to get my 1 back here. One of them is going to need to be negative, and one of them is going to need to be positive. Well, I want a negative 2x and a positive 1x so that they sum up to get me a negative x in the middle. So that is how you factor this quadratic down. So because this quadratic factors this way, then it's also going to factor, but instead of x, it's going to be 2 sine x plus 1. And instead of x minus 1, it's going to be the sine of x minus 1. So I know all that factoring that you did in pre-calculus and algebra 2, hopefully it's paying off because we're going to still use it. So now we've factored this equation. I'm going to set each factor equal to 0. Okay, so I get down to kind of that final value where the sine of x equals something and the sine of x equals something. So sine of x is equal to negative 1/2. So I'm going to look kind of right on my sheet here, on my unit circle, and I'm looking for the sine of x is equal to negative 1/2. So I've got 7 pi over 6, and then I've got 11 pi over 6. And those are within the bounds of 0 to 2 pi. So I've already got those answers, 7 pi over 6, 11 pi over 6. The sine of x is equal to 1, so that happens up here and nowhere else. So I get x is equal to pi over 2. So these are the three solutions that work for the equation that was given to me. And if I wanted to, right, I could plug each of these in and verify that they do work correctly. Or I could go jump over to Desmos. Why don't we do that? Open up another Desmos tab. So you can see what I'm talking about. So I want to make sure that I'm in radian mode, and I'm going to change my step to pi over 2. And let's type in our equation. So we've got 2 sine squared x. Okay. Minus the sine of x. Okay, and we're looking for it to equal 0. So we're just looking at when does it hit our x-axis. So again, we've got our pi over 2, our 7 pi over 6, and our 11 pi over 6. So you can see this is when this equation is equal to 0. And now we have verified. It might be a little bit easier to verify on Desmos this way rather than plugging each angle back into the equation. But that is always an option as well. All right, let's look at our next one. This one's getting a little bit tricky. What I notice when I see this is I have both a sine and a cosine, and that is no bueno. We do not want two different trig functions unless we can have a GCF. Remember when we had cotangent x as it was in there as well as cosine squared? Well, we will able to factor out the cotangent because it existed in both terms. In this case, we do not have a common term between all three of these terms, and I know this looks like something that I feel like I'm going to need to factor. I'm going to need to reverse FOIL. So here's what we're going to do. Remember that old identity, sine squared x plus cosine squared x equals 1, one of the most fundamental identities that we have in trigonometry? Well, I'm going to solve for sine squared x. So I get that sine squared x is equal to 1 minus cosine squared x. So I'm going to go back over here to my equation, and wherever I see a sine squared x, I'm going to replace it with 1 minus cosine squared x. Okay, I'm going to distribute this through. So I get 2 minus 2 cosine squared x. It's equal to 0. Now I want to combine my like terms, so I'm going to do 2 minus 3, so I get negative 2 cosine squared x plus 3 cosine x minus 1 equals 0. Now here's the thing. I hate dealing with a negative x squared. So I'm going to multiply both my left side and my right side, every single term, by a negative 1. Remember, the rules of algebra say as long as you do it to both sides of the equation and to every single term, you haven't broken the rules of algebra. All right, so now I have gotten this down to something that I'm a little bit more familiar with. And what I'm going to do, I'm going to pull this aside here and say, okay, let's consider 2x squared minus 3x plus 1. How is this going to factor down? I know I've got a 2x and an x and a 1 and a 1, and they both should have the same term, and that term is a negative. All these rules. If you want to set up your x marks a spot and go through that process, you definitely can. I'm hoping, though, with all of the factoring that we've done, we can take some of these little shortcuts here. So I'm going to come back over here. We get 2 cosine x minus 1 and cosine x minus 1. So those are my two factors. I'm going to set each factor equal to 0. So over here, I get the cosine of x is equal to 1/2. And over here, I get the cosine of x is equal to 1. So now I just need to figure out on my interval here. Oh, no, there's no interval. So we've got to do the whole multiples thing. So the cosine of x is equal to 1/2. So up here, right, I've got pi over 3. Where's another one? Then we got 5 pi over 3. So I've got both of those to consider on this map. Cosine of x equal to 1, well, that happens just at x equals 0. Okay, so here's what my solutions are going to be. X is going to be equal to pi over 3 plus 2 pi n, because I've got to do all the coterminal angles with this one, and I can't pick up 5 pi over 3 in the same way. So then I have to do 5 pi over 3 plus 2 pi n, and then I need to do 0 plus 2 pi n, or you could just say 2 pi n. So these are all three of the solutions, because it wasn't within a certain interval, that I have to consider. All right, we now have an interval set up for us, okay? I do see I have both a cosine and a sine, which again is no bueno. We don't like that. So what I'm going to do, I am going to square both sides. Okay, so we're going to square this side and we're going to square this side. Now by squaring the left side, that means I am going to have to FOIL this. I know, a lot going on here. So on my left-hand side, I wind up with cosine squared x plus 2 cosine x plus 1 equals sine squared x. Well, in our previous example, remember our previous example, we took sine squared x and made it equal to 1 minus cosine squared x. So I'm going to take that value and plug that in over here. Hopefully all will be revealed as to why we're doing this. Okay, now I want to set everything equal to 0, so I'm going to subtract 1 from both sides, and I'm going to add cosine squared x to both sides. So I get 2 cosine squared x plus 2 cosine x equals 0. I now can factor out my GCF because now I have cosines in both places. Remember, always try to look for a GCF if possible. So once I do that, I now have my two factors. I can set them equal to 0. So on this one, I get the cosine of x has to be equal to 0. And over here, I get the cosine of x is equal to -1. And because I'm looking for just solutions within an interval, I can just use my unit circle and say, okay, where is the cosine of x equal to 1? Or sorry, equal to 0? We got pi over 2 and 3 pi over 2. So that's going to be 2 of my answers. I'm going to write them down. Now we have cosine of x is equal to -1. Well, that happens right here at pi. So my final answer here is pi over 2, 3 pi over 2, and pi. Okay, so we're going to amp it up a little bit here. We're going to involve multiple different angles in the forms of like cosine 2x, cosine 3x. So what we're going to do is we're going to figure out the angle, and then from that angle, we're going to continue to solve. Let me show you what I mean by that. So example 7 here. We want to get cosine x, or cosine t, in this case all by itself. It's got a 3 attached to it, so that's just going to have to be what we isolate. We want to get that all by itself. So I'm going to add 1, and then I'm going to divide by 2. So I get the cosine of 3t is equal to 1/2. So let's think about this for a second. I don't have my unit circle over here. Let me give it a copy so we can... It kind of covers up our question there. So we want to know for what angle, so angles with a cosine of 1/2. So angles that have a cosine of 1/2, we got pi over 3 and then we've got 5 pi over 3. All right, so those are our two answers. So we would say that 3t equals pi over 3 and 3t equals 5 pi over 3. But I want to solve for the actual value of t. I don't want to solve for 3t. So I need to multiply both sides by 1/3 or divide by 3. So I get t equals pi over 9. Same thing over here. I'm going to multiply by 1/3. Or t equals 5 pi over 9. And since I'm not in an interval, right, I want to make sure that I consider all of the multiples. You'll notice I am dividing these as well by 3 because, right, if I'd set this up, I would have said really 3t is equal to pi over 3 plus any of its multiples. So when I multiply by 1/3, I have to multiply both of these parts by 1/3. So that is my answer there. Right, let's look at example 8 here. We got 3 tan x over 2 plus 3 is equal to 0. So I need to get this all by itself. So I'm going to subtract 3 and then divide both sides by 3. So I get the tangent of x over 2 is equal to -1. So tan is -1 at 3 pi over 4, right? Let's just verify that. Yep, 3 pi over 4, we've got it. And also 7 pi over 4. But what I can do is I can say 3 pi over 4 plus any multiple of just pi. Instead of multiples of 2 pi, we've got just n pi. So we know x over 2 is equal to that value. Well, I now need to multiply everything by 2. So I'm solving for x. So I get x is equal to 6 pi over 4, which simplifies down to 3 pi over 2 plus 2n pi. So I think it's probably better if when you set up these and then solve, you include the multiples when you need to. I should have done that on the previous example. You include that so that when you simplify everything down, you're including that as well. All right, let's look at example 9. At some point, right, we're going to try to use our unit circle as much as possible. But what happens if we start to get some values that are not on our unit circle? What do we do at that point? So let's start here. Notice I have both a secant squared and a tan x, which we know that's not good, right? We need to have everything in the same terms if possible. Secant squared x is equal to 1 plus tangent squared x. That's one of our Pythagorean identities. So I am going to take this value here and plug it in for secant squared. So I get 1 plus tan squared x minus 2 tan x is equal to 4. I'm going to want to move the 4 over, right? So I'm going to subtract 4 from both sides. I'm going to combine my like terms. So I get tangent squared x minus 2 tangent x minus 3 equals 0. Now I might do a little kind of aside here, right? I've got an x squared minus 2x minus 3 equals 0. So what 2 multiply to give me? We've got x minus 3, x plus 1. So that's how this is going to factor. So I get the tan of x minus 3, and then the tan of x plus 1. So I'm going to set each of these equal to 0. So I get the tan of x is equal to 3, and the tan of x is equal to -1. All right, so the tangent of x equaling -1, remember tan is sine divided by cosine, so we've got up here and down here. So I can cover that by saying 3 pi over 4 plus pi n. Okay. The problem is tangent is not 3, remember, inverse tangent is here and here. So what we actually want to do is not use 3 pi over 4, but use instead negative pi over 4. We're going to use this one as our main angle. I know, and that's a little trickeration. Honestly, I think if on a test you use 3 pi over 4, it would be perfectly fine. But remember, we do have to include those requirements there. So that solves that one. Now, tangent of x equaling 3, that is not on our unit circle, but it does exist. Tangent, remember if you think about tangent, our range for tangent goes from negative infinity up to positive infinity. So we can get a tangent value of 3. So all you have to do in that case is say x is equal, and you can use arctan or inverse tan, whichever notation you like best, plus n pi. And those are our two solutions. This one, not on unit circle. This one on unit circle. But using restrictions. All right, so we've got 2 more examples to go. I know this is a very tough lecture. So in this example, I apologize, but it cannot be factored nicely. You must use quadratic formula. Okay, I know, not too fun. But in this case, when we set it up, we're not going to be solving for x, we're going to be solving for the sine of x. So if you want to think about it right, it's x squared minus 3x minus 2. So my a value is equal to 1, my b value is negative 3, and my c value is negative 2. So sine of x equals opposite b plus or minus the square root of b squared minus 4ac all over 2a. There we go. So instead of it x equaling opposite b, it's x sine of x equals opposite b plus or minus the square root. Okay, so we do this out. We get the sine of x is equal to 3 plus or minus the square root of 17 all over 2. And if that wasn't complicated enough, it's about to get more complicated. So what I'm going to do is I'm going to figure out what both of these values are. So I'm going to do 3 plus the square root of 17 over 2, 3 minus the square root of 17 over 2 to get these decimal approximations. So this one up here is 3.5616. This one here is negative 0.5616. Okay, so these are the values of sine of x. Okay, they are not the values of x, they are the values of sine of x. Now, the sine of any angle can never be greater than 1. So this value here has no solution. So this one we don't have to worry about. Now in this case, there is a value, so we can consider it this way, right? We want to figure out, okay, x is equal to arc sine or inverse sine, however you want to write it. I wanted to show it both ways, of negative 0.5616. We've got to figure out what are those values, okay? This ends up being outside of the bounds. This ends up being negative 0.5963. That's not what we're looking for. So what I'm gonna do is I'm gonna jump over to Desmos to kind of show you what I mean. So here's what we did. We know we've got sine of x, so I just graphed the sine of x here. Now the other thing we know is that the y value, or the sine, when we calculate the sine of x, we need to get out that negative 0.5616, that value of the quadratic formula that we saw. So we're trying to figure out what are the angles, what are the values of x's that meet that requirement, that have an output of negative 0.5616. So I graphed y equals negative 0.5616, just like at the beginning of our notes, and I'm trying to figure out where they intersect. What is the x value for this interception point? Notice, right, negative 5616, or negative 0.5612 here are the y values. Our x values are 3.738 and 5.687. So those are our solutions. Very, very tricky. On your homework, you can definitely just write it out this way, right? You can just write out the arc sign or inverse sign or whichever notation you like. You can write it out that way. Our actual solutions that we just saw is 3.738 and 5.687. So those are the real solutions that we saw. But on your homework, if you just want to write out arc sign, inverse sign of whatever the value is, that is completely acceptable as well. This was a tricky question. All right, our last one of the day, of a very challenging lecture, is to use a word problem, okay? So we've got a surface area problem of a honeycomb cell, and these can get very difficult to try to figure out. Notice we've got a picture of our honeycomb over here on the right, and yes, the diagram is supposed to help us, but let's look at it. So the surface area of a honeycomb cell is given by that formula there. Notice it has both cosine theta and sine theta. And theta is kind of the angle up here that is created with this apex, with this kind of highest point here. And we want to figure out if the height value is 2.4 inches and our S value is 0.75 inches, kind of our, I don't know, width, whatever we want to call here, what value of the angle will give the minimum surface area? So you notice we're not plugging in values for theta here. We want to figure out what angle of theta will give us the minimum surface. So we're going to have to use Desmos on this one, or your calculator. Notice they want the answer to be in degrees. So if we're using our calculator, we need to be in degree mode. If we're using Desmos, and I'll show you how, we also need to be in degree mode because by default, Desmos is in radians. So we know our H value is 2.4, S value 0.75. So I'm going to plug that into my equation here. So I get 6 times 2.4 times 0.75 plus 1.5 times 0.75 squared times the square root of 3 cosine theta. Okay, so I get S is equal to 10.8 plus 0.84375 times the square root of 3 minus cosine theta over sine theta. Okay, so that is my equation. And I just want to figure out at what value of theta will I get the smallest value of surface area. And so when we put this into Desmos or your calculator, your theta is going to equal your x value. Your s value is the output or the y value. X, so remember the angle is your input, the y value is your output, and that represents the surface area. So we've got our equation, and really all we have to do, this is going to look a little bit funky. We're going to jump over to Desmos. So I've already put this equation into Desmos. Notice it's got a lot going on. It's a really funky picture here. And what I'm trying to do is between 0 and 90 degrees. So let me show you how I did this. Under the settings button, you need to make sure that you have degree highlighted. So all I really care about is this little sliver here, from 0 to 90. What is the smallest value that we get? And usually what Desmos will do, it'll kind of help you find that minimum point. So my minimum angle that will give me the smallest amount of surface area, which is about 12, is a 54.74 degrees. So that is my answer to this question. So I get my minimum theta value is approximately 54.74 degrees. So that represents the minimum angle to give me the smallest amount of surface area. Thank you for your time.